penso che tu devi cercare di parlare su sto microfono qua per lo streaming, cioè prende bene da lontano.
Ma ha detto questo che di usare questo.
E basta che non vai là, dovrebbe funzionare.
Sì.
Dai, comincio a tradurti perché
Sì.
arriverà. So welcome everybody. It's a pleasure for me to welcome today's speaker, who's Alessandro Alberto Trani from University of Tokyo. Alessandro got his PhD from SISA in 2017. Then he got a prestigious JSPS fellowship, Japanese National Fellowship, and he joined the group of Michiko Fuji, Professor Michiko Fuji at University of Tokyo, where he is now. Well, now he is here, but usually works at the University of Tokyo. Alessandro is a dynamicist, so he investigates whatever is related to dynamics, including Tyson binaries, galactic center dynamics of stars, gas, and other objects. And today he's gonna talk about scatterings on a sphere.
Yeah,
Thank you.
Random title. So, let me start by introducing my interest. So, at the moment I have three main lines of research. The first one is the gas dynamics close to supermassive black hole, and was the not most recent papers I published. And long story short, I simulate molecular gas in the center of galaxies to understand how molecular clouds can get disrupted by the tidal field of supermassive black hole, what are their morphological properties, and in the end, in 2 words, what I found is basically the impact of the nuclear star cluster potential can affect also the gas morphology, and this can tell us something about the sphere of influence of the supermassive black hole in other galaxies. And so you can see from this plot here, these trajectories, in a near Keplerian potential, the orbits are near Keplerian, so where the supermassive black hole is dominating, while when the nuclear star cluster is dominating at the center of galaxy, your orbits are more like harmonic-like, and so this affects how the gas is distributes around the supermassive black hole, so forms a disk in a supermassive black hole dominated environment, and forms a ring in a nuclear star cluster dominated environment. And in the end, this paper was featured by the American Astronomical Society, so it made me very happy. The second topic I like to work on, as the main topic of this seminar, is free-body dynamics around supermassive black hole. I will talk more about later. And the third one is dynamical modeling of planets. So planetary systems, in the end, is not surprised. Dynamical supermassive black hole is Keplerian, so we use the same numerical tools and same mathematical models to describe planets around a star. So I have a few collaborators here. One of the works I've done is to investigate the dynamical stability of this, the second known transiting multi-planet system in a star cluster, the Presepe cluster. And unfortunately, this is a multi-transiting system, so it tells you that it's coplanar, and so it's kind of boring system. In fact, it was found outside the half-mass radius of the cluster, so it likely was not perturbed. But an interesting feature of this system is there is some kind of resonance between the outer planet orbit and the inner planet orbit, and there is this kind of semi-circulation of the axial lines. So here you can see the star is here, these are 2 orbits, and there is this secular exchange of angular momentum. The outer one oscillates, the inclination oscillates along with time, and also the axial line precesses, and they semi-circulate, in the sense that the angle between these 2 vectors is always between 0 and pi, never goes around the circle. So another interesting question I'm trying to solve with Adrian Hammers from Princeton and Aaron Geller from Northwestern University is, can a hot Jupiter have an exomoon? So in other words, can a hexamoon survive the migration process of its hot-to-be Jupiter? And will a moon allow for the migration of a hot Jupiter? So I'm just briefly mentioning these things, and there is, if you want, you can ask me later. And another very interesting topic on the planetary side of things is the formation of ultra-short period planets, in the sense there are this category of planets that are below one day. Their period is below 1 day, and it's even shorter than hot Jupiters. And we don't know their origin. They cannot form at less than 1 day in the star, so they cannot have not been born there in situ, so they must have migrated there somehow. So I'm trying to investigate if maybe because I lead off, like in this movie, this is the interaction of two planetary orbits, and the inner one starts to get eccentric, and tides kick in and circularize and shrink the orbit of the inner one. But there are also several other scenarios, and each scenario will give different properties of the system, and now it's very timely to investigate this topic, because there is a test, the satellite, that will find many ultra-short period planets around very bright stars, so you can do a follow-up with radial velocity and find if there is a massive planet further out. And this is it. I'm also lead developer of a tsunami code for planetary and stellar black hole dynamics. And also, I worked on the tidal module in the 7 stellar population synthesis code. This is the main reason I'm interested in tides. So let's begin with the main topic. So scatterings of Earth sphere, which means three-body encounters around supermassive black hole. So are there three-body encounters around supermassive black hole? What does it mean? So let's start from some observational facts. There are young massive stars that orbit the supermassive black hole in our galaxy, and also M31, or nearest spiral galaxy. And there are young stars, so many young stars come in binaries. Also, there are some validated binaries in our galactic center, but these binaries are not alone. They are surrounded by a cusp of stars. These cusps can be visible, like this infrared image of our galactic center. This is the cusp of the high density cusp in the center of our galaxy, but there can be also a hidden cusp of compact remnants that sink towards the center and form a high density cusp around the supermassive black hole. So we have a high stellar density. We have also some binaries around supermassive black holes, and this is the perfect recipe to have close binary single encounters. So this is how it looks like in this kind of plot. So there is the supermassive black hole. It does not participate in the encounter. It just provides the tidal potential in which all the other objects move. There is a binary which is incoming. There is another object. Can be a stellar mass black hole. Can be another star. There is an encounter and then an outcome, of course. In this case, the binary is ionized or it's broken up. So why do we care about this process? This is it actually has several implications. So the first, astronomical. I first investigated these mechanisms to explain the origin of the S stars in the galactic center. So these the innermost stars that orbit the supermassive black hole in our galactic center. There is also a statistical implication, in the sense that nobody really cares nowadays, but there is a long history of studying the three-body problem that goes back to D'Alembert and Lagrange. And there are still many open questions about the outcome, the statistical outcome of a three-body problem. And now with better integrators, we are able to crank up the statistics and actually test statistical theories. And also there is a gravitational implication, in the sense of gravitational waves. So these three-body encounters can actually trigger or maybe prevent the coalescence of binary black holes in the center of galaxies. So let's start with the first astronomical implication. So with this mechanism, we can break up binaries. So three-body encounter, the binary is broken up, and these two objects can get scattered on a highly eccentric orbit about the supermassive black hole. we do see highly eccentric orbits, highly eccentric objects around a supermassive black hole in our galaxy. One group of these kind of objects are the S-stars. They are these very eccentric stars, the innermost 30 stars that orbit a supermassive black hole in our galaxy. And there are also these enigmatic G objects. They are, we don't really know what they are, but they are on an extremely high eccentric orbit around a supermassive black hole. So they cannot form on this extremely eccentric orbit like this, so they must have migrated somehow. And we have also some constraints of the timescale for this migration to happen. And the most recent ones is from spectroscopy, and it's about 10 million years. So these stars seems to be young, so this poses some constraints on the migration process. And the most interesting fact is that the S-stars, with these, if you believe this estimate, seem to have the same, more or less the same age of a disk of stars that is farther out. And this disk of stars is made by O-type stars, while the S-stars are B-type stars. So the question is, can we model the same, these two different populations with the same, actually as the same population, simply these B-type stars were scattered from the disk with Tribonian encounters. So to solve this, to have an answer, I ran many simulations using this tsunami code. I've developed in collaboration with Mario Spera, and has this is lots of technical details, but not needed. The bottom line is very fast and very accurate, and has tides, post-Newtonian, and Python interface and rebound support. And also have run a large set of Tribonian encounters around the supermassive black hole. Here is the shopping list of the initial conditions. The most important thing is that I'm modeling two populations. So the B-type binaries, so between 8 and 14 solar masses, so they match the S-stars in our galactic center. And also the O-type Wolf-Rayet stars. They are more massive, and they match the disk of stars that is also observed in our galactic center. And this is, again, the initial conditions in a eccentricity versus semi-major axis plot. These are all the position of the observed S-stars and G objects. There are two, one here and one there. And so these initial conditions match the observation of the clockwise disk in our galactic center. So let's give it an encounter. And these binaries will scatter, and some will get broken, like these red dots. They get on high eccentric orbit. Some will remain more or less in this region, which are the flybys. So the binary is not breaking up, is not even getting a strong kick from the stellar mass black hole they're encountering. And there can be also exchanges, of course. So if we now count how many stars, S-stars, can we reproduce with this mechanism, we can find about 12 S-stars and the G2 object. So not all of them, of course. And what about these S-stars that are very in the inner zone of the galactic center, very close to the supermassive black hole, the very small semi-major axis? We cannot match these S-stars if we start with a disk that is truncated up to here and down to there. And the only way to reproduce all the S-stars is to extend the original disk. So the broken up binaries, the broken binary components can get highly eccentric, but their semi-major axis will more or less remain the same as the initial one. So if you extend the disk down to, let's say, 0.006 parsecs, we can reproduce also this population. But the problem is that we don't see the disk up to here nowadays. So it's difficult to reproduce all the stars with a single model. And another way to look at this is to see this plot. Is the probability density function of the outcome of the scatterings. So initially, all the stars reside in this bump here, this Gaussian at low mild eccentricity. And after the distribution, after the encounter of all stars, the ionized one and the one still in binary is this green one that has. So this Gaussian becomes a tail. It becomes has a tail, at high eccentricity. If we remove the Gaussian component that still matches the original one, we can get a distribution, a high eccentric tail that matches the S stars. The problem is this bump will remain nonetheless. So far we can explain only 12 S stars by three-body breakup. The number seems to be fairly reasonable in the sense that to have these 12 S stars in the region that we can match, we predict we must have had at least 86 B-type stars in binaries in the galactic center. And if we can reproduce all the S stars, but we need to extend the disk, and we have a problem. This is in tension with current observations, unless we find a mechanism to destroy the disk. So for this is eventually the end of this topic, and we can think more about the statistical implication of the Keplerian three-body encounter. So what I've told so far is an unbound binary single encounter. So there is a binary, there is a single that comes in, and they are unbound. There is a usually a very short encounter, exchange of energy, angular momentum, and then you have an outcome. But there is also another kind of three-body systems, the bound systems that are unstable triples. So, and now I will focus more on the statistical theories, the statistical escape theories of these bound systems. So, we know that there is no stable three-body system that is not hierarchical. So, any triple system that is not hierarchical will be unstable and will decay in a binary and a single, as here. And we can describe basically this breakup, this decay, by the kick velocity that will be formed when the binary and the single decouple, and also the same major axis on the eccentricity. And most recently, there has been some findings using simulation that not just the energy of the initial triple is affecting the final distribution, but also the angular momentum of the initial triple. And this will come up later. And we have a statistical theory to describe this kind of systems. It was developed by Monaghan. It was also the same person that developed the smoothed particle hydrodynamics scheme, by the way. And so, for example, what we can do in a supermassive black hole environment is to put these triples, put them around a supermassive black hole orbiting, and see what is the impact of the tidal field. So we study this three-body breakup in this tidal field flavor. And one of the properties that we can look at, for example, is the triple lifetime, of course. And this is the distribution of breakup times for several initial conditions. So we have the isolated ones that form this tail here, and they all break up early, but they can form a very long tail. This is actually in tension with the statistical theory, because the statistical theory predicts exponential decay. So this is already something that is not very well explained by theory. But if we add a tidal field, so this triple will decay faster, so they will get broken up, because the tidal field will help breaking these binaries, these triples. But we can also take a look at the kick distribution, so the kick between the binary and the single. This is the statistical theory prediction. This is this line. This is the result from the simulation. They fairly match. We can put the same triples around a supermassive black hole. We see if they are very far, they will basically behave like an isolated one if the tidal field is not strong enough. If we put them closer to a supermassive black hole, the tidal field will start to have an effect. And you see that the kick distribution, the velocity distribution, is shifting towards the low end of the spectrum. And if you put these triples even closer, this is what is going to happen. So this can also be explained by simple analytical calculation by the fact that since the system is now totally limited, the tidal field is actually helping the triple to break up. So the triple can make less work, and so the kick to break up the triple can be lower, because the part of the energy will be provided by the tidal field. And we can look not just at the magnitude of the kick velocity, but also at the distribution, the orientation distribution of the kicks. So this is basically the distribution of orientation. Here color-coded is the magnitude of the kick. Here, basically, we can orient this map with the orbit of the triple around the supermassive black hole. So this is the progress direction. So with the triple, so is aligned with the triple orbital vector about supermassive black hole. This is the radial towards supermassive black hole. This is the anti-radial. This is anti-normal and normal. And this is the retrograde. So in this case, the distribution is completely isotropic, is as in isolation. But if we move this, we put the triple closer in to the supermassive black hole, we can start to see some deviation from anisotropy. And what happens is the radial ejections, so when the triple breaks up towards the radial directions, are mostly favored. And while prograde and retrograde directions are disfavored. And this also has a very reasonable explanation, in the sense that in this case, the triple direction, the breakup direction, is mapping the Hill sphere of the triple, which is not a sphere, of course, is more aligned, is towards the is oblate towards the radial direction, so opens up toward the radial direction. So the energy barrier to escape towards the radial direction is lower. That's why there are more escapes and breakups towards the radial direction. Well, the escape barrier is higher in the prograde and in the normal retrograde directions. And we can also take a look at the properties of the remaining band, the eccentricity distribution, so major axis and eccentricity, one minus eccentricity. And the colors are for isolated, black, and red is the triples that are closer in to the supermassive black hole. The semi-major axis distribution doesn't seem to be very, very different, but you can see that it slowly moves toward a higher semi-major axis. And the eccentricity distribution is actually changing quite a lot. And by the way, it's already initially, so this is the isolated one, this is already super thermal. So this is something that initially we could not explain very well. So why the outcome of a triple interaction is super thermal. And the problem is that we were starting from no angular momentum triples, so very low angular momentum. So there is not enough angular momentum to distribute among the binary and the single. And so there is a lack of angular momentum, and in the end, the final binary is super thermal. There is not enough angular momentum. And by adding the tidal field, the triple can interact with the tidal field and gain angular momentum. And so the distribution starts to become more and more thermal, which is what we expect from let's say, Jeans theory. And yeah, we can also explain why the upper limit of the same major axis increases, because from basic conservation of energy, the tidal field, the system will be tidally limited, so we can say that the Hill radius is what is tidally limiting our triple. And so this is the largest semi-major axis that an intermediate state can have. So when the binary and the single are loosely bound. And we can check the same thing for high angular momentum triples, and we see that there is a completely different outcome. So the same major axis distribution is quite different. So depending on the tidal field, and while the eccentric distribution does not change at all. This is again due to the angular momentum exchange between the tripole and the tidal field. So what happens is that these triples here have interacted with the tidal field and lost angular momentum. So they are behaving more like low angular momentum triples. And there is this, we can check, for example, in this plot, which is the final angular momentum divided by the initial one. So in an isolated case, they all stay in 1, because the angular momentum, of course, is conserved. If they gain angular momentum from the tidal field, they get here. If they lose angular momentum, they get here. And the final, the binaries that get lower, say, major axis, are the ones that also lose the most angular momentum to the tidal field. So this is a small summary of what I've said so far. So unstable three-body systems are affected by the tidal field especially when the Hill velocity is, which is the typical velocity at the Hill radius of the tripole, is comparable to the kick velocity of the tripole. So the typical velocity of the kick velocity of the kick breakup, the velocity breakup. And there are several properties that are affected, from tripole lifetimes and the kick velocity distribution and kick orientation distributions. And also the final binaries properties change. And this is interesting by itself and can give us lots of insights on the statistical theory of escape, of three-body escape, and can also have some other interesting implications for more realistic scenarios, such as gravitational wave mergers. Why? Because we see that encounters by themselves, they can change the orbital properties of a binary. So, for example, here is this distribution of eccentricity. This is the initial one. This is after one encounter. You can see the encounter generally they increase the eccentricity of binaries. So this can have an impact on the gravitational merger timescale. And also, and this is the cumulative distribution of gravitational merger timescale. So you can see that while initially they have up to 1,000 years, here they can merge very quickly.
Sorry, in the previous plot, the eccentricity, you include also exchanges there?
No. Only binaries that
yeah.
Only flybys. Yes. And this is just very example. Of course, this is not something new. This happens in star cluster as well. There is nothing new about three-body encounter in a supermassive black hole, except this. So there is some kind of artifact here. But anyway, this is the cumulative fraction of three-body encounter. So in this case, I took, say, 10 to the 6, 10 to the 5 binaries. I let them have a three-body encounter around a supermassive black hole. And afterwards, I take the same binaries and I put them in isolation. So I simulate the same encounter with the same extra properties, so impact parameters and velocity dispersion, but in isolation. And what we see is that since the eccentricity is excited by the tidal field, the final distribution of merger time will be lower. So you can see this is the comparison between the Keplerian case and the isolated case, and there is some difference. So this is already something new that we did not know a priori. And of course, all these numerical experiments are just with one single encounter. But what happens is that these binaries can have lots of encounters in the center of our galaxy. And you can see here, for example, the encounter rate per million year as a function of distance from the supermassive black hole, assuming there is a cusp that is more or less follows the same density distribution of the stars. But so far, the only mechanism that's been considered for merging binary black holes around a supermassive black hole is a quasi-Lidov mechanism. So there is plenty of literature investigating the quasi-Lidov mechanism of binary black holes around supermassive black holes. And they all treat binaries as isolated. So, but this is not the case. And the encounter rate can be very high. It can be even comparable to the, or shorter than the cosine of timescale. And so what I've done, what I'm doing now, is I've developed a kind of Monte Carlo code to simulate and follow the evolution of binaries around supermassive black holes. And what I'm interested in to follow the causality of evolution, so the isolated evolution, so as if the binary was actually isolated. So, and then you can have these causality of cycles, but also the encounter part. So whenever we predict there is an encounter, we can just switch, add a particle to our integration and simulate an encounter and follow whatever is remaining out of it. So this is the Monte Carlo code I've made. It's based on Python and has it uses Tsunami as the main integrator, of course, and just does all the Monte Carlo part in a friendly interface in Python, and then calls the C++ code. This is, for example, this is a comparison of the same initial conditions, same initial binary, with switching off the encounters and turning them on. So this is the same major axis and eccentricity as a function of time. And you can see here the quasi-lead of evolution doesn't exchange energy. So the same major axis is flat, does not change, while the same major axis is changing after each encounter. So each of these bumps are small encounters that exchange some energy. And in the end, there is an encounter that pumps up the eccentricity, and in the end, this binary is merging. While in the previous case, if we were only considering the causality of evolution, the binary would not merge. Of course, this is only an outcome. There are also several bad outcomes for the sake of gravitational wave emission, in the sense that the binary can be broken up by the encounter. And so, what is the final outcome? What is the balance between breakups and mergers? I don't know yet. Also, this depends a lot on our density distribution that we assume about supermassive black hole, about the cusp distribution, the dark remnant distribution, their average masses. And so I'm running more simulation at this very moment. And I still expect there will be an enhanced merger rate with respect to previous studies that only consider causality of mechanism, despite the many binaries that will actually break. So I hope that this work will change the current paradigm that is the causality of mechanism of binaries that induces gravitational wave mergers in galactic nuclei. So I think I was quite fast. So if you have any questions, I have many slides that I can talk about a bit more. Yeah, switch.
Thank you, Alessandro. So are there any questions for Alessandro? Yeah, Alessandro.
Just a very quick question. I'm not sure I understood correctly. Promenade?
Yes.
What does it do? It just randomly injects encounter?
Yes,
somehow, yes.
I had basically the same question. So what are the criteria, physical criteria to decide when these encounters happen?
Okay. So the base system, base evolution is isolated one. So there is the binary and there is the supermassive black hole. The binary just orbits the supermassive black hole. But at the same time, at some time steps, it checks for the collision rate with a simple n sigma v prescriptions from a pre-calculated density profile. So computes the density profile, computes the stellar mass distribution of two components, so the cusp and the dark remnants and the stars. And then generates a random number. If this random number is lower than the probability for to happen, and it starts an encounter, and there will be generated an encountering interloping stars on the same orbit of the binary. And after the encounter is finished, with some criteria that is basically they're not interacting anymore. Anyway, there is no stable triple system, so eventually they will break up. And then follows and then removes the outer body, and it will continue the isolated evolution. Now it does everything integrated. So what I could do to speed up things is to use a kind of average secular evolution for the isolated part, like average the equations, but I don't think it's really necessary, and still has some inaccuracy.
So you just want to integrate the encounter part
and use a secular evolution code like the one they are using in US. But this is just really to speed up things and lose some accuracy, and I don't know if it's really worth it. And what I could do also is to let also the cusp evolve, so have a kind of evolving density profile, and this will be a complication. This is just the beginning, and of course it's not limited to binaries and black holes. What I'd like to do is also to add some stellar evolution to simulate binaries in the galactic center, stellar binaries, and see what is their survival rate, for example. Which is
spoiled also my second question.
Yeah.
What would change? So you start from a triple system that are already black holes.
Black holes, yeah, simple case. Yeah.
What would happen if you add also stellar evolution?
Yeah. There is now a recent paper by Alexander Stefan on the binaries they still don't consider the encounters, but they have binary evolution and secular averaged evolution. So So what will change? So they say that, for example, when one of the stars evolves, there will be tides, of course, and the system will shrink or merge usually. So I don't think it's really exciting. I mean, it's normal. I would expect this, and the nice thing is I can put directly the tides inside the three-body code, the n-body code. So yeah, and since it's written in Python, it's very easy to just incorporate stuff that is written in a nice way and can be wrapped in something, in a high-level language. I could use a muse to have the stellar evolution, for example. Right.
Ricardo?
So I'm not expert in this, so
Yeah.
it'll be a very question. So I guess you have a distribution of masses for these black holes. Let's speak directly about black holes. And you have a distribution of merging time to merge. So there are systems that have a short merging time, which are interesting for gravitational wave, of course. And if you only consider your initial distribution, so without this supermassive black hole effect, you will have a distribution, a certain probability that
Yes.
the emergent binary detecting gravitational wave has black holes with a certain mass and not another, or a certain mass ratio as well. How strong is the impact of this environment, where you also consider the presence in the distribution of masses that you detect in gravitational waves?
In the
And
distribution
at which distance do you have to be to have an important effect
Yeah.
on? You see what I?
Yeah. You also mean on the final masses of the merger or the final masses of the complex remnants, let's say in binary evolutions picture?
Of the merger, no.
On the merger. Okay. On the masses, I don't have a quick answer. I don't think the masses will. This is a good question. I don't have a straightforward answer for this.
Are the masses? Is it this effect very sensitive to the masses of the components of your binaries?
It's more related to the supermassive black hole, and well, if you have encounters, in this case, you can also have. I think you can have exchanges, and you can build up the mass of your compact remnant. So, in the sense that you will end up with more massive binaries, just because you are removing the light ones. Yeah. Yes, and the distribution of times, for example, we will easily remove all the white binaries because they will get broken up somehow by and also depending on the distance from the supermassive black hole, because there is not just the encounter rate is depending on the distance from the supermassive black hole, but also the velocity dispersion distribution. And the higher the velocity, the easier that you destroy well, not easier, actually there is a sweet spot in between. So it's, yeah, there are many factors, but it will alter a lot, it alters a lot, especially not just the encounter, but if you put everything together. So the causality of evolution, that will definitely merge your binaries that are eccentric enough, or they're in an interesting inclination with respect to the orbital plane about supermassive black hole. And yeah, there will be an interesting interplay. For example, an encounter can tilt your binary around the orbital plane about supermassive black hole, triggering causality of evolution, and the binary can merge eventually. And these things cannot happen in isolation.
Is it correct to say that, just a very basic sense, that if you are very close to a supermassive black hole, you increase the probability that all the merging binaries there have on average a higher mass?
Yeah.
Is it too easy to...
Maybe too easy, yeah. And also,
What do you think?
So maybe we can discuss it later in class.
Also, yeah, well, yeah. I have seen many breakups in my results so far. So
the point is that if you have an encounter at a typical speed of a galactic centering in the central parsec, this encounter is more than 100 kilometers per second. It means that you break most of the binaries. So it's a very disruptive encounter, which is not good for gravitational waves. On the other hand, I think the dominant effect here is the escape velocity. You are deep in the potential well of the galaxy, so the escape velocity is very high, which means that if some binaries manage to survive this hostile environment and merge in black hole binary, you have a second generation black hole, and the gravitational recoil kick that it gets is not sufficient to eject it from the system. So if you are very lucky and you build up another binary, you may have a particularly massive binary. But it's really fine-tuning, because on one end you have the best condition of escape velocity, on the other hand this is a hostile environment for binaries. So
yeah, it's close to supermassive black hole. You have lots of just
there's no big trend that it's equal.
Yeah, no, there are so many different factors that have a strong interplay within each other. You can also have like mergers with you can also, the breakup actually can also trigger a merger with a supermassive black hole itself, in the sense that one of the binary components.
It's very good for
Yes. I have already seen some in some of my preliminary results.
Consider dedicating a paper to that. We are now in the stage of deciding the scientific cases for LISA, so it might be very important. Other comments, questions? I have a question about the first topic, stars. Do you think that, well, the clockwise disk is a clockwise disk, but it's also quite a complex structure, and there are small star clusters, compact star clusters in there. You think considering these star clusters could change the results of your analysis?
Do you mean the star cluster?
In the clockwise disk you have also IRS 16,
these things.
Compact
Yes. The problem is they're still too farther out, so I don't think they're going to. This thing, we don't even know very well where they are. These.
More than 1.
Yes.
So not inside the clockwise disk.
In projection, maybe, but. I mean, it would be nice if they find O-type stars within the 0.01 parsecs. This is the main issue.
Yeah, no, maybe we discuss it
Okay.
later while I was thinking of the class. Other question? Well, if you don't have any question now, Alessandro will be visiting us for today and tomorrow, so you can find him around. Currently he's in my office, maybe then he will move to Sarah's office, so first floor. I suppose now we are going for lunch, so you are very welcome also to join us for lunch. And let's thank again Alessandro.
It's 0.08 parsec.
0.08.
0.08. So it's.
Oh.
No, because you need a two-step process. That's the point. He does not form so many interesting orbits because all of these encounter and destroy the binaries.
Thanks.
You need some body encounter that
I'm
leaves
not
the
familiar
binary.
with it.
Yeah, don't worry. It's a bit, especially the middle part is a bit, nobody really cares about the statistical theory of three-body systems. No.
So you're not going to stay for the weekend now?
Hmm?
When are you flying back?
In June, but I will go back to my place in
Okay, your
at
hometown.
the end, in Friday, yes.
This Friday.
This Friday, yeah.
Okay.
Yeah. Tomorrow, yeah. I'm just staying here one night, then tomorrow I go.
If you don't mind?
Yeah, of course.
I can join you
Of
for
course,
lunch.
you should join, definitely.